Hello, everyone. Thank you for coming. I'm Mathias, and in the next 45 minutes, I will introduce you to a project that I'm very excited about. It's called Swave, and it's a Reactive Streams infrastructure toolkit for Scala. But before we dive into the content, a quick show of hands. Who of you would say that you have a rough idea of what reactive streams are? Excellent. Almost everyone. Who has no idea of reactive streams? No one. Wow. This is catching on. Very nice. Who has played with Akka Stream so far? At least played. Wow. Cool. Very nice. Because I'm not going to be really talking about reactive streams in any great detail. There's lots of material already online, and you know it anyway. But we will still spend the first part of the talk on looking at where in the general streaming world this fits in and why you might be interested in it. All right. So as you know, since you've all been using reactive streams already, there is quite a lot of excitement about stream processing in general in the recent years, much more than for 10, 20 years ago. And there are a few key drivers why that's the case. And clearly, one big driver is the big data that we now have. We really do have more data than we used to. We're dealing with masses of video streams, audio streams, tweet streams, machine learning, training data, and all kinds of stuff that doesn't fit into memory. And for these types of applications, stream processing lends itself naturally. OK, so that's one driver. But there are other drivers as well, because stream processing is a very nice and general programming abstraction that helps us in the new challenges, or with the challenges in the distributed and concurrent programming environment that we find ourselves in now much more than 10 years ago, and in 20 years or 10 years that will change even more. So we always need a powerful and general programming abstraction, and that's why things like Swave and many of the other tools that you have played with exist. Now, when we look at what is out there in the space, there's really a ton of stuff. You can't really name them all. I've just put down two things on the left there. But if you look at what is available in the stream processing world, then you can put them on a chart like this, where we have on the left tools that are more geared for the distributed scenario. So for the scenario we have really big problems that you need to scale across several machines. Then there is the space in the middle where you say, OK, stream processing between two things or several things that live maybe on different threads. And then we can really go to the very right, where we become really local, so within one thread. And there's very little. So we can ask ourselves, why is everything that's available, all the big tools, mostly targeted at the distributed scenario? And it's simply because that's where the problems are the hardest traditionally, where you have the most data and where you just need to scale across machines. And those solutions are usually quite big, they're complicated, they're very powerful, but they are just something that you wouldn't just use for a quick job, in one thread, let me sort some stuff. You wouldn't fire up a Spark cluster for that, clearly. Now, where does Reactive Streams fit in? Reactive Streams, as you know, is just a standard. It's not a solution. It's a protocol. It's a protocol for just defining how to hand data between a producer and a consumer in a proper way that allows them both to run in their own time and space, completely asynchronously and without any blocking. That's the idea, right? So as such, it doesn't really fit on this chart in one corner, because it doesn't concern itself whether the producer or the consumer and the consumer live on different nodes and different threads, or maybe on the same thread. So that's why it's the whole area. And if we look at solutions like Akka Stream, then there's traditionally, or their core focus was, so far, the inter-thread solution. So within one machine, the concurrent scenario, we have a producer that maybe lives on a different thread than the consumer, and how do we use that properly? And my guess would be that maybe in the future we'll see Akka Stream develop a little bit further to the left, because it naturally lends itself there. Swave, on the other hand, has a focus, also the core focus for the inter-thread scenario, but actually my goal is to move it further to the right, because there's value to be captured there as well, so it becomes small. And that's why I've always also put down the Scala Collections on this chart. They're not a streaming solution so far, but it's what we use when we are on our thread. In our small, local environment where everything is ours, we tend to use lists, vectors, and whatnot. And that's a space that's interesting also for a streaming solution. Now, since we're contrasting a bit collections and streams, or streaming solutions, let's understand that a bit further, because it's quite important to really know what we're talking about. So the Scala collections are really the workhorse that we use all the time. And what us, or at least me, and probably you as well, is very attractive, or what we are very attracted to, is code like this. Very concise code. That's Scala collections. That's how we want to write our business logic. It's concise, it's expressive, there's no boilerplate, it's easy to read and maintain. That's great. That's also the gateway drug into Scala for many people that come maybe from Java, because that's cool. And that's what I like to keep like that, and maybe expand on that, give it more power. But this is the code that I would like to write. So what is interesting, when we look at how we deal with collections, then the approaches that we choose when we write collection-based code, they're really shaped by the experience that we had so far, our heritage, so to speak. And since many of us probably come from a Java or imperative background, who would say that you have a imperative Java-like background? Most, yeah. So let me just give a small example. How would you generate 10 random strings? Say you need them for a test. You just need to cycle through 10 random strings. And the point is not how do you create a random string, but more like how do you generate 10 of them and kind of, encapsulate them so that you can use them. Take a second to think about how you would do that, like for yourself. If you come fresh from the Java world, maybe you would reach for something like that. Perfectly fine. You create a buffer, you add 10 strings, done. Then you have the 10 strings right there. Works, no problem with that. Of course, in the Scala world, it's a little bit frowned upon because of the explicit mutability that we have there. Okay, so maybe if you know Scala a bit more and you know the collections library, you'll probably reach for something like that. There's a fancy method called fill that kind of hides it all away, and you get a method that's already filled with 10 random strings. Cool, that's good, right? But there's also another solution available with the Scala collections that you can use, and that's this. That's available. You don't need to import anything or depend on any library. There's Scala immutable stream that you can use, and that is a streaming-based approach. So you first create with stream continually an infinite stream of random strings, and then you just take the first 10. So that works just the same. Who would have used the approach at the bottom? A few, right? A few. But I think those tools are actually underused a little bit, because they are cool. They have benefits. In this scenario, for example, for 10, it doesn't really matter, but suppose you need to generate 1 million strings. If you go for the list approach, then you will actually need the memory for 1 million strings, because they will be pre-allocated, everything will be filled, that will take some time, and then you'll cycle through them. In the approach at the bottom, you don't need any memory. You just create a description of what you want, and then it gets pulled out and generated as you need it, so it's lazy. And there are many scenarios where that's actually a better approach. It's just different thinking. And my point here is that stream-based solutions are not really confined to applications where you really deal with large amounts of clearly streaming data, like video streams or audio streams. There are many, many applications of stream-based solutions in your ordinary code that you write every day that you just don't see because you're not used to it. And many times, they're better. They can be better. They're not necessarily always better, but it's good to have in mind that there might be a stream-based solution somewhere around the corner, right? And that's the area that Swave is targeting. Kind of explore that, give you more tools in that space. Okay, when we look at stream-based transformations, or stream transformations, then we can really group them into 5 different areas. There are 5 basic types of stream transformations that you have. There is a simple map, for example. You have a stream, you apply a transformation, you get back another stream. Then there is something that we call fan-in, where you have several streams that with some kind of logic get merged into one. Merge might be one, but there might be other strategies for how you, merge those data. And the opposite is a fan-out, where you have one upstream and several downstreams, and some logic that distributes the incoming elements. And then there are two types of interesting stream-of-stream operations. One that I call inject, which takes a stream of elements and produces a stream of elements. So every element that comes out of this transformation is itself a stream that has elements. Just you can nest streams like you can nest lists or any other type of abstractions. And then, of course, you need a way to flatten those out again. So those are the 5 basic types of stream transformations. And we already use them. On the collections, they're available. You can group all the things that you can use on the collections into those 5 things. So they're not something new or strange, but you don't necessarily think about them in that way. I won't go through all of them. You'll recognize them, but that's what they do, essentially. So there's a close relationship between streams and collections, and we need to understand better like how they really relate. So one important distinction is, of course, strict versus lazy collections. My guess is that most of us use the strict ones much more. That's the go-to tool that we just reach for, like list, vector, set, map, and so on. But there are 2 types of lazy collections that Scala already gives us, which is immutable stream and iterator. Collection iterator exists, and you can use that. Most of you probably have done that before. And if we contrast them, then the strict ones are really about storage. It's about having something. As we said before, the list is there, it exists, and I can just use it. We have storage for that. And the lazy ones, they don't have any storage. It's more about transformation. That's the idea, right? So I describe a way for how I want my data to be transformed, rather than they're stored here in this format and then stored in another format somewhere else. And because the strict ones are storage-based, they really kind of stand alone. Once I have a list, I can do whatever I want with it. And the lazy collections, they really get their power when you connect the transformations, rather than look at them in isolation. We can connect them to pipelines and graphs and really big things, as you can do with Akka Stream. Of course, the strict ones, because memory is bounded, the strict ones need to be bounded, and the other ones can be potentially unbounded, even totally infinite, like the stream of all natural numbers, for example. Because they're storage-based, the strict ones are repeatable automatically. If they're immutable, I can just look at them as often as I want. And for the lazy ones, there's immutable stream, which is repeatable, because it's immutable, but iterator is consumed. When you use it, it's spent, and you need to recreate it in order to be able to go through it again. Okay, so there's important distinctions between the two. Now, what the Reactive Streams protocol allows, and what Swave implements, is really a generalization of lazy collections. What does that mean? It's something more powerful, or you could say it differently. Lazy collections are essentially a special kind of what reactive streams allow. So a subset of everything that you can build with reactive streams are in fact lazy collections. What is important is it's not the other way around. It's not that reactive streams are always lazy collections, right? One is a subset. So let's contrast lazy collections and Swave versus or reactive streams, what they allow. Lazy collections, they're always synchronous. Right? They always run, they never dispatch to any other thread. They always run on your thread. If you ask a stream or an iterator to give you the next element, then that will happen on your thread. Reactive Streams allows both synchronous as well as asynchronous operations. And that's what Swave also does. Then, because it's not active, the lazy collections, you always need to pull. Whereas Reactive Streams allows a dynamic push-pull. And you probably heard that before in other presentations or introduction material. I won't go into details what exactly that is, but it allows active components to push if they're active, right? Lazy collections usually never lose elements. Unless you really mess around with an iterator, you shouldn't lose any elements. Now, if you're in the Reactive Streams world, it might happen that you don't observe all elements. Maybe because you're not fast enough. right? If you're consuming the Twitter fire hose, then it's probably a good thing if you don't have to consume everything, right? But generally, this doesn't happen just out of the blue. Normally, you should know when there's a risk that stuff might disappear. For example, the Twitter fire hose end might tell you, if you can't keep up, we'll drop elements. All right, then it's up to you to kind of build something that can keep up with it. So, but it might happen. In the general case, maybe you are too late to subscribe to a stream, and there might be elements already gone by. It's live. It might be a live thing. Lazy collections, they have really a linear thing, a linear DSL, a very simple one. If you look at immutable stream, then you can map, flat map, and those things. But there's no graph, really. Whereas with Akka stream, as you know, you can build graphs, arbitrarily large ones, and it's more modular. You can kind of draw boxes and reuse them. If you have a lazy collection, like a number of transformations on a immutable stream, then that's really opaque. You just get back a stream. There's nothing you can inspect. With Akka stream and also with Swave, you can actually look inside of that transformation chain, as we'll see later, and kind of inspect what is happening. Like, what is this graph, this pipeline, what does it consist of? Which is very helpful if you want to debug and other things. And as we said before, iterators can be consumed or is consumed always, whereas immutable stream is repeatable. And in Akka, as you know, generally components try to be reusable, but you don't know necessarily that they always are reusable. It might be, for example, if they wrap a socket on the network, then the data that come out of there, if they're not buffered, if you're not actively buffering them, then they're not repeatable. So you don't really know. In Swave, everything will always be consumed. So you always need to recreate everything. So there's no question about whether it's reusable or not. It's just never reusable, just like a future or an iterator. We'll see. So before we dive into an example, these are the API basics. Basically, we have a stream, a pipe, and a drain, which roughly corresponds to what Akka calls source, flow, and sink. And the reason why I gave it different names so far is because I assume that you will often have both on your class path. And just to make interoperability easier, different names are kind of helpful. This might not always be like that, but currently that's what it is. So there's a Swave core stream, which is similar to the source. There's a pipe, which is similar to the flow. And there's a drain, which is similar to the sink. And as you can see already here, there's no additional type parameter like you have it in Akka stream, where there's the materialization value as type parameter. This doesn't exist in Swave, and we'll see that later why that's the case. OK, so now let's actually switch to an example. So some of you might know this example. I've used that several times already. It's a basic, very basic simulation where we just say, OK, we want to simulate pi, and or estimate pi, and we do that with the Monte Carlo method. So we generate random points in this unit square, and then we just look, are we inside of a circle or aren't we on the outside? So in which area are we? And then by counting the samples that we have, we can approximate pi in a very simple way. So that's just a moderately interesting example. The goal is to build something like a streaming operation or stream-based application that exercises all types of stream transformations as we've seen them before. So we want to exercise fan-ins, fan-outs, stream of streams, and so on. So I implemented this. You can implement that in Scala if you want to in a few lines. Maybe that's a nice small task for yourself. How can you implement that in the shortest way, for example, with the collections? So the goal here is not to build something that's really short, but just build something that works and exercises as much as possible. OK, so this is the translation into a stream graph. So we start by generating random double values, infinite stream of random double values. So that's the elements that come out of here will be doubles. And then we do a group into two, so we get back the stream elements will be a sec of doubles. Then we can map to a point, which is a case class. So now we have a semantic value x and y values. That's the point inside the unit square. And then we just do a fan out, just in order to do a fan out. Then we have two branches. One, we're filtering whether the point is in the circle, and on the other side, we filter if it's not in the circle. Then we map once more, and then we fan in with a merge. So both branches get merged back in. And we end up with a common supertype of inner sample and outer sample, which is sample. And then we do a scan operation that you might know from the collections. It's the same kind of logic, similar to a fold, but it actually emits every element. We drop the first, then we inject. So we create a stream of streams and let the next element decide when to end an inner stream. So we map across the stream of state. This is actually not quite right. Well, it's true. The stream elements is a stream of state. So we have a stream of state. So we always drop 1 million and take 1. Basically, we just want to see every millionth element. That's what we want to see. All the others we just drop. So we let the simulation run, and every millionth element we're interested in. Then we flatten the opposite of the inject. We map to a string. We take a certain number, and then we just say for each print line. So what this does, when it runs, it just instantiates the graph. It will run, and after a million samples have run, we'll see a line pop up. And it will continue running until, in this case, 10 lines will print. So let's see. So that's the app. That's all it is, nothing else. We start by importing this. That's all you need to do, really, most of the time. Then this line gives us a streaming environment. It's pretty similar to an actor system that you know from Akka. It just gives you, the kind of all-encompassing world on the outside. It contains configurations and dispatchers and everything that you probably need. Then we instantiate a random, and we start off with this one. So we have a continue, that's the stream that we've just seen, random next double. We group, we map. This is a fan out. We'll see later how exactly that works, but basically it allows you to write in a fluent way your graph. With Akka Stream, you can't really do that in that world. You need to break out and kind of use the graph DSL to build a graph like that. With Swave, for many simple graphs, even more complicated ones, you can use a fluent DSL to write that up. So here, this is the first branch, and that's the second branch that we've seen. And here we say, OK, now we want to merge that. We scan, we drop, we inject. That's exactly as it was just on the chart. So that's the nice thing. We can draw the logic on a whiteboard and then translate that into code almost one by one, one-to-one. And that's great. So we flatten concat, we map, we take 50 in this case, and then we for each print line. Now, what is interesting here is all of this runs on the caller thread, because there's nothing in there that requires asynchronous dispatch necessarily. There's no operation in there that needs a concept of time, for example. If you put in a throttle that somehow says, OK, every 100 milliseconds I only allow one element, for example, then you need asynchronous dispatch, because there will be a timing question. But here, there is nothing like that. So if there's nothing that requires asynchronous dispatch, and you don't actively tell it to dispatch to some dispatcher, then it won't. It'll just run on your thread. So once this is all completed, then we just print total time, and we measure the throughput. OK, so let's see. So I compile. I have a nice alias, so everything is good. And then I just run main. So let's see what happens. And as you see, it starts, and it approximates pi like that. Actually, the technique, the Monte Carlo technique, is pretty crappy for approximating pi, because it's exponential. If you want one more digit of accuracy, you need to run 10 times as many samples. So you don't really get very far. But it helps us here, and it shows, OK, the 50 million samples will go through the total thing in 16 seconds, so we have about 3 million elements per second that we can shoot through this. So that gives us a rough indication for what the performance is of how this thing can run. Just so maybe let's look at the same thing in Akka Stream. So this is basically the same example, just in Akka Stream. It looks very similar. There's a little bit of different stuff. For example, the broadcast filter merge part, I had to write like this. There might be another way to do this now, but this is how you do it. So that's basically the diamond in between that we had there. And we can use split when here, which creates a stream of streams and so on. And we can do concat substreams. That's a new new way that allows everything to run in a fused fashion. And we'll take 30. So if we want to, we can also run that. So let's see how that works. This will now need to dispatch. It won't run on your caller thread, because that's not what Akka Stream does. But it's configured in a way to run as fast as it can on one thread alone, so with as little dispatch as possible. And you see, it's not that there's no that much of a difference. Currently it's about maybe half the throughput, but that doesn't really say much, because as usual, this is not a proper benchmark, and we don't really know where this difference comes from. There might be some components that are actually faster than on the other side, and so on. So this is a very, very artificial one kind of thing. But for this application, we can see that Swave is about twice as fast. If we go to, let's go back to the example and turn it asynchronously. So turn it into something async. So if we want to make this now, let's say we want to actually parallelize this. Currently, it's not parallelized. It runs all in one thread, as we said. We could, for example, add an asynchronous boundary here. And we could say, OK, let's split the whole pipeline into two parts. The upper part runs in its own thread, or thread pool, and the lower part also. So we could put an asynchronous boundary at that point. So that makes everything be dispatched. Now, in order to be able to then look at those things, we need to change a few things. So, for example, I'll print down here when the main thread exits, because it will immediately exit. And we need to, so if we look at this, for example, what the type of this is, then IntelliJ tells us this is a future of unit. So this actually produces something at the end. It's a future of unit. There's no result. But the future will be completed when everything is done. So, and we use that signal to print our end result. So here we need to import two new things that we hadn't had before. That's fine. So we only, because it's slower, we only do 30. OK, then because we're here, we're doing an onComplete, and that needs an executor. So dispatcher, we need to import one more thing, which is the default dispatcher, which is pretty much similar to what you have in Akka. So let's see whether that runs. See whether it compiles first. Might be something missing. Nope. So let's run it. So it still runs, but as we said, we split the pipeline in two relatively easily just by saying we want an asynchronous boundary at that point. And now two things can run in parallel. Theoretically, it could be faster. But in fact, it's a bit slower because the overhead of the asynchronous boundary at this point outweighs the benefits of parallelization, because those things are so lightweight that a single thread can actually do it faster. Now, in your real-world applications, you probably are going to have more heavyweight transformations, and then the parallelization might buy you something. But it's important. This shows it's important to not just slap in asynchronous boundaries at some point, but place them consciously and maybe tune a little bit. Try taking them out, putting at them different positions to see for your applications and your load what's the best way to parallelize this stream. But the key point is that you have very high-level tools to say exactly where you want those asynchronous boundaries. If you contrast that, for example, with an actor-based application, then this is much more low-level. Then you would have to really, think first, where do you want it, and then write everything so that you have an asynchronous boundary at that point. If you want to move it somewhere else, then that's a major undertaking in an actor-based application. Here, it's very simple. I just move the line, two lines down. That's it. So that's the kind of high-level power that I'm looking for, or that we all like in the collections. And this basically gives you everything that the collections already have, plus more. That's where the generalization is, and that's where the sexiness comes from. OK, so let's move on. That was a demo. Now let's look at the DSL basics a bit more. So the basics, as we've seen before, so the simple one is you have a stream, you attach a few transformations, and then you can do, you say to and a drain, and that gives you a packaged stream that's not running yet, but everything is set up. And all you need to do is push the button and say go, and that's what you do with run. Pretty similar to what you have with Akka Stream, where you set up the blueprint first, and then when you say run, it will materialize and actually do the running. When you change or separate those steps like that, it gives us the ability, for example, to take the ready-to-be-run description of the graph and not run it, but maybe inspect it, maybe do something with it, as we'll see. So how do fan-ins work? So if you have a fan-in, then you can do something like that. This shows the logic of this. If you have a stream, you can call attach, and you can take other streams and attach them, and you get like a bunch of open streams. And you can define in which order they should be attached, but there are a bunch of open streams, and if you have several open, you can call .fanin concat, for example, and that will concatenate and merge them all. Or you could say fanin merge or fanin whatever. There are several different logic alternatives for how you can merge streams, but that's a simple fan-in, right? So that's how the DSL works there. You can also have heterogeneous fan-ins, so they don't all have to have the same type. If they have different types, like here, for example, we have a stream of strings, we attach an int stream and a float stream, so you have 3 different streams open, and then you could say fan-in to tuple, and that would create a stream of the tuple of those 3 things. You could also fan into an H-list, you can fan into a product, which is nice, because that's just a case class, and Swave relies on shapeless to kind of do all the boilerplate underneath, so you don't have to concern yourselves with actually creating those case classes. You just attach those streams, and the fan into product will take one of everything, and once it has from every upstream one value, it will create a case class instance and push that downstream. That's helpful. You can also do fan into a sum type. For example, when you have a stream of lefts and a stream of rights, you can actually merge them into a stream of either. So that's nice. So we have fan-ins, heterogeneous or homogeneous as you want. This is the same kind of idea here. Now let's look at the other side. How does a fan-out work? Fan-out is a bit more, might seem initially a bit more difficult. So if you have a fan-out, you call fan-out broadcast. And that gives you the ability to say .sub, and that attaches a substream. So one of the branches underneath. And then you can just continue writing whatever you would want to write on that sub-branch. And then in the end, you have two possibilities. You can either say to drain, which kind of sinks this stream away to somewhere, or you can leave it open by just saying .end. If you leave it open, it will just stay open. And there are several ways to deal with those open streams. One of them is, for example, you could just, at the end, you just say continue, which allows you to, if you have a single open stream, to just continue writing your DSL with the one open substream that you left open, as is the case here. And the order doesn't matter. It could be, you could have the one that's open as the first or the second or whatever you want, because sometimes the order matters. If you have several substreams open, then you get into a situation where you can mix fan in and fan out, and that's what we had in our example right before. So here, for example, we have this kind of situation. You have a fan out, we attach a substream, do something with it, and then leave it open. Then we attach an external integer stream, and we can have another sub to the fan-out broadcast here, for example. So this one is just another attachment to this one, and we'll just sync it just for fun to ignore. And that's what I show here. You can also attach something from the outside on the left if you want, right? So that you can kind of plug and play this thing together how you want it. And then at the end, we could just say fan into tuple, for example, and that ends up with a stream of a tuple of float, string, and int. And so what this is supposed to show is that it's quite flexible of how you can, create fan-ins and work with them, and then maybe take a subset of the open substreams that you have and kind of merge them in and pipe them somewhere else. And so that's it's nice because the idea is, as I've said in the beginning, is to allow you to write very concise code with a very little boilerplate. So this is powerful enough to allow you to write a lot of the graphs that you would maybe sometimes need to construct by hand now with one DSL. It's not powerful enough to create all kinds of graphs. There are some situations, for example, when you have recursion, where you can't only rely on that. So there's something else that we need in order to be arbitrarily powerful. And that's just a simple coupling. A coupling is just a piece of pipe that you can freely connect from both sides. Once you have that, you can construct anything. And here in this example, it's actually a bit involved. It's not a lot of code, but let's see what is the output of this small snippet. So we have a stream of ints, 1, 2, 3, and we concat, which is just a simpler way of saying, have a fanon, attach one, and then do flatten concat. So we attach the output piece of the coupling, all right, afterwards. And then we fan out broadcast with 2 substreams. The first one, in the first substream underneath the fan out, we take the first element, we add 3, and then we attach it to the input of the coupling. Okay, so there's your loop. There's a loop there. Can you see that loop? Yeah? Okay. And here we just say, we attach another output to the fan out, and we say we want to continue writing with that. It's just a shortcut for attaching an empty substream and do continue. And then we do for each print line. So what's the output going to be? So it's 1, 2, 3, 4. Yeah, 1, 2, 3, 4, that's the idea. If I run this, I want to see 1, 2, 3, 4, because the first one that goes in here is going to be a 1. We add 3, and then concatenate that at the end. So it should be 1, 2, 3, 4. Now, when you run this, it doesn't do anything. Now, why is that? And that's the purpose of this example is to show you that there are some tricky bits about streaming that you probably have noticed maybe already in your working with Aka Stream. Sometimes it's not quite as easy to see where there's a problem. Now, why does this deadlock? The reason is the fan-out broadcast here will only request from its upstream if both of its substreams signal that they want something, signal demand. Otherwise, it won't signal to its upstream, give me an element. Now, one of its substreams, the first one, actually feeds back on top of the broadcast. So it will only demand if the fan-out demands, but the fan-out will not demand until it demands, you see? So there is in this loop that we've created, there's just no demand. And if there's no demand, nothing will run. So once we have realized that, we also see how we can fix this. We just need to add a buffer. Just a buffer element of size 1 is enough to generate the initial bit of demand that we need to get the cycle going, right? Now, that's not something that is very easy to see in the beginning if you're not used to how those things work. And in our work on Akka HTTP with Akka Stream, we had several times situations like that, where you set up a nice fancy pipeline and a big graph, and you start it, and for some reason, it doesn't behave as you want. So it's important to be able to inspect what is happening, to visualize maybe even the state of this graph and this pipeline. Like, where is the pressure in the hose, so to speak, and where is no pressure? Once you see that, it's easy. Right? If you have a visualization of the state of this graph in its runnable shape, it becomes easy to see. If you don't have it, you need to build it in your head, and then that's tough. I'll show you more on that in a second. There's more that I could be talking about in terms of the DSL and how Swave gives you features that are helpful. For example, one important thing that you probably already used with Akka Stream is the ability to group a piece of your total graph together, give it a name, and kind of encapsulate it. So that you say, OK, this setup, I'll just draw a fence around it, give it a name, and kind of store it away, so that you can build composable layers and become more and more high level without having to build everything in one go. That exists in Swave, and it's called modules. We won't have time to go into that. But there are several types. There are forward modules that only go forward. There are ones that you maybe know from Akka Stream as well, which is called BD flow, where you have two things that go in opposite directions, as is often the case when you work with network, for example. So we could be talking about this, but we don't have time. There's a test kit and so on. There's one thing that I want to still go into, because this is important to me: debugging, inspection, and rendering. So let's go back to our example that we had here and change it so that we can actually render it. So what we do is take this away, and we just say, this. So we don't run it, we just create the whole thing. So we do it, we attach a drain, and we give it a name called val piping, for example. So that's the piping. That's the type of this whole thing. If I ask idea what the type is, it's a piping is just the name of a runnable graph. And what we want to do is we want to see what it looks like. There's a method called currently pipe element render. It's just, don't worry about the names, they might change, but the idea is we want to render the structure of the graph and look at it. So let's see whether it compiles. Probably doesn't, because I still have unused imports here. One good thing that I always do now in my project is I always enable fatal warnings, because that really helps. So the compiler will not actually compile if I have a warning, and there's a warning in there if I have unused imports. So this works. So it puts out an ASCII rendering, an ASCII graph of what this pipeline looks like. Now, it's not extremely pretty here, but you can see exactly what we had before. You can now see this on your console in ASCII art, so to speak. So here it's rendered in 7-bit 7-bit ASCII. The core point is to give every element in your stream, every transformation, its own line, so that we have space to actually attach attributes and do whatnot. And render, there's a complete graph renderer implemented here that can render arbitrary graphs in ASCII art like that. And I thought I can do that in 3 days, but it took a lot longer, let me tell you that. Yeah. So, for example, here's another example. This is the coupling example we had before, but this time rendered with a different type of glyph set, as I call it, which is kind of like the font. And this is, for example, a 2x2 UTF-8 rendering. So every little element in the graph is 2x2, and it's UTF-8. And it looks much prettier than if you do a 7-bit ASCII rendering. And you can just influence that yourself. You can pick your, there are a few predefined kind of ways to render a graph. You can define your own, and then you have complete freedom what you want to show for every transformation. Now, this is the basic stuff that we need in order to be able to do exactly what I said before, show the current state of the pipeline when it's running. So currently that's not yet implemented, but it's not much anymore to actually, at runtime, render this and, for example, color according to pressure. So that you can see in this color example, there's no pressure, right? Which means there's a deadlock. That's the reason for the deadlock. And that's the idea behind this rendering. So that's one, for example, one interesting feature in Swave. The basic design goals were, so far, really runtime performance. So just be fast, because that's what everyone wants. Even though you don't need it, you still want it to be fast. That's just the way it is. And the synchronous mode is really crucial. We need to explore more how far we can push this, like what exactly we can really run synchronously on the caller thread. But if you don't need to dispatch and you can run synchronously, then you really move into the space that is currently occupied all by the collections that we use on our local thread. Because then the overhead becomes really, really small, and we can reach for those tools where we would otherwise reach for, vectors, lists, and so on. That's the idea. The DSL is supposed to be as concise as possible without, sacrificing too much readability, and of course it's a trade-off, so that's the first idea. We want it to be lightweight, no dependencies, or as few dependencies as possible. Currently there's basically only shapeless. There's, for example, no akka, and debuggability, very important, because we've been through the crap. Okay, quick comparison, Swave versus akka streams. Akka stream Swave is non-lifted, as we've said before, so everything runs once and is consumed. Stream is lifted. Swave can be synchronous or asynchronous, depending on what you need, what you want. Stream is always async, which means Stream runs on actors underneath, which of course run on executors, and Swave runs either on the caller thread or on executors. The Swave is Scala only, so there's no Java side, which has benefits. Not to everyone, but especially for the maintainers, it has certain serious benefits. The DSL is shapeless based for Swave. On Stream, we currently have a combination of a fluent DSL and a graph DSL. And the point is that my goal is to have something that we can innovate quickly on. That could just, because the space is so new, there's so much to still explore and learn, that it's great to have something that we can just change, that we're not really bound by binary compatibility and long-term support and so on, but just be able to try out things, because it's tremendously interesting and attractive. A quick comparison to understand what the lifted versus non-lifted means. Basically, in Swave, the DSL creates directly the runnable structure. It's single use, but it's inspectable. In Stream, the DSL creates a blueprint, which is reusable and inspectable, and that gets materialized into the runnable structure. And you can see how the stuff on the left side might be faster in certain situations, depending on whether you're rematerializing an existing blueprint or not. And of course, there are benefits to having a blueprint. So this is not an invalid approach at all. It's a very valid approach for Stream. It's just, with Swave, we want to explore the other side. What happens if we don't have blueprints? Like, what can we do? What can we not do? The roadmap, I just released version 0.5 M1 this morning. It's on Maven Central. You can go play with it. Next, we need documentation, documentation, and documentation. That's the next big thing. There are a few remaining holes in terms of operations, and we need more performance tuning. And of course, we can add all kinds of features, but we want to get the core right. There's one small thing I want to, before we finish, I want to point to. The development process for this, I also decided that we want to change this a little bit over what we had, for example, with Spray, where we didn't quite manage to really expand the core maintainer group as much as would maybe have been beneficial. So this time, we'll try that. Collective code construction contract is something that Peter Hinchins, that you might know, has written up for 0MQ, where it worked exceptionally well. We're going to try that here. So the core thing is to just make it very easy for contributors to come on board, become maintainers, and really drive this forward. Resources, you can find them, you know them probably. Thank you very much. If we still have time for quick questions, I think the time is up, but does anyone have questions? Yes?
So, quick one about the asynchronous. Wasn't it supposed to be, Streams supposed to be either asynchronous or possibly synchronous? I mean, from the blueprint, you could possibly build two versions.
You probably could, yeah. It's not something that is currently in there, and I don't know whether that was ever really a target or a goal, or maybe, yeah. We could ask the Akka team whether that's potentially interesting or not. But it's definitely not impossible to materialize the blueprint to something that runs synchronously. That's true. It's just not currently something that I don't know whether it's a goal or not. Anyone else? Yes?
How does it compare to Monix?
To Monix, yes. How does it compare to Monix is the question. I don't know. Good question. I haven't had time to really look at Monix. I know it exists, so that's another example that there is lots of interest in this space, and I think it's good if we have more implementations, right? We need more people on this, explore it, because it's tremendously interesting. I guess we'll see much more of this in the future, and so the more projects we have, the more we can learn from each other. So we don't actually see each other as competitors at all. It's more like explore the space together in different ways. That's the basic idea. Thank you.